Lesson 6.3 is on exponential functions. These are nonlinear functions in the form y equals a times b to the x power. A and b should be numbers that we know, and x is the variable that changes, just like y equals mx plus b. We can plug in a number for x, and we should be able to get an answer for y, and those are our ordered pairs we would plot on a graph. So an exponential function has really 4 different patterns it can look like. They all have roughly the same curve shape to them. Exponential functions represent a repeated multiplying pattern. So we're going to learn that a represents the starting value, b represents the multiplying factor, the common factor, the ratio we use, and x is how many times we multiply by that common ratio. The first very basic type of problem we're going to do is decide if a relation is linear or exponential. So here I've got 2 tables. These are 2 separate problems. So what we're going to do is we're going to compare changes between the 2 sides of the table. So what's happening is y increases. Well, 2 to 4 can either be plus 2 or times 2. But what happens to the next way, or to the next spot on the table? 4 to 6 can either be plus 2 or times 1.5. Times 2 would get us to 8, not to 6. So it's got to be an adding pattern because that's the one that was consistent. This adds by 2 each time. It's an adding pattern. So that's what I would say. Adding pattern. Then I'd call it linear. This is what we were looking at all of first semester, was linear relations. Over here, as x goes up 1 each time, let's see what happens to y. At first it's plus 4 or times 2, and then it would be plus 8 or times 2. So this time the multiplying was the one that stayed consistent. It's doubling each time. 16 times 2 would get us to 32 as well. So this is a multiplying pattern, and I would call it exponential. This is how we identify whether or not we're working with an exponential graph. Is it an adding pattern or is it a multiplying pattern? Here we've got our next type of problem. This is evaluating an exponential function. So first thing to note is that these are in that y equals a times b to the x. You will oftentimes see b in parentheses. So what we do is we plug 3 in for x. So I have y equals negative 2 times 5 to the 3rd power. Now order of operations says I have to do this first. Exponents before multiplying. Getting negative 10, then doing the exponent is wrong and will get you a much bigger number than you want for this problem. So I would do 5 times 5 times 5 first, which is 125. Now I multiply. Negative 2 times 125 is negative 250. If I multiply first, I get negative 10. Then negative 10 cubed is going to get me negative 1,000. Obviously much different than negative 250. So the way to know you're right is if you're correctly following order of operations, exponents before multiplying. Do your exponent part first. Now we'll head over here. Now I've got an exponent of negative 2. Do you remember what we do with that? We've got to go back to our properties from 6.1. We take the reciprocal of that piece to get it to be a positive exponent. You can also put this in a calculator directly as negative 2. This is just a nice little refresher for us. So now it's to the positive 2, and I know how to do that. That's just multiply by 0.5 twice. So that's 0.25, or 1/4. 3 over 0.25, that's going to come out to 12. All right, so we're just plugging in our exponent for x. You could plug this in exactly as you see it into a calculator and get an answer. You can do the same thing over here. But sometimes doing it in our heads, doing mental math, doing it by hand, reinforces what we're trying to learn. So that's evaluating exponentials. When we get to graphing, we'll use a slightly different strategy that'll be faster than calculating it every individual time. So let's look at what graphs of exponentials are going to look like. First off, our most basic one is going to be this. This red line never actually crosses over here. And this graph is going to happen when b is greater than 1, and also when a is greater than 0. So let's do some quick numbers that match that. This would be like y equals 2, 3 to the x. If we make a negative, what's going to happen is all of our answers are going to be negative. So we would flip down to this side of the graph. So we've got a second one, and I'll do a dashed line to show that they're meant to be different graphs. This is when a is less than 0. Okay. So one little reminder when we're looking at a graph like this, reading left to right means as we go forward in time. So when b is greater than 0, things are growing to larger numbers. I understand that this is going further and further negative, but it's a larger negative number. It's growing, not shrinking. In this situation, shrinking refers to getting close to 0. So if we look over at the other graph, things shrink. We have exponential decay when b is between 0 and 1. That's what this inequality means, is b is between 0 and 1. If b is a fraction, we're losing a percentage of our money, population, whatever, over time. So the a part is the same. A negative a means we're going to end up down here. One thing you should always expect to see, though, is a positive b value. This is not going to make sense if b is a negative, because then we would be going all over the place. It hardly makes sense. We will never use b as a negative for an exponential function. It doesn't make sense for what exponential functions are supposed to represent. So a can be negative. This would be like, let's come up with something. If I push a buoy underwater, this would be it coming back up to the surface. The further underwater you push it, the faster it's going to throw itself back up to the surface. So then 0 would be like the surface of the water. Just trying to come up with a reason we might use a negative for this. All right. This one over here might be like unpaid credit card debt. The longer you go without paying it off, the more and more it grows, because the more money that's there, the more the interest is going to add up in pure dollars you owe someone. Okay. So these are the 4 possible shapes. They all look fairly similar, but they're at different directions based on what a and b values are. Let's do a couple of graphs. This first one is going to be y equals, or f of x equals 4 times 2 to the x power. So before I do anything, let me just draw out here. This is a positive a is greater than 0, and b is greater than 1, which means it's our normal it's going to have roughly that shape. Without even knowing where any of the points are, I'm just doing that. That's the picture I have in my mind. That's what it should look like, which is why I made my coordinate grid have nothing below the x-axis, because I should never plot any points under there when a is positive. All right, so my strategy for this is to fill out a table of values, x and f of x. This is also y. That'll be y on our graph. This is the x-axis. This is f of x, the result of x. And I like to go from -2 to +2. This is actually really easy to do once you get the hang of it. Understanding it's important too, obviously. But let's start with what happens when I plug in 0. What's anything with an exponent of 0? It should be 1. So this comes out to 4 times 1, or just 4. A is always going to be your starting point. So whatever value is in A's position should just go right here in the 0 slot. That is a hard fact, a truth. So we get the point 0, 4 out of that, 0, 4. So I got what my first point plotted. All right. So from here on out, that's going to be our initial value. Initial value. All right. And then B is our multiplying pattern. So we multiply forwards, times 2, times 2. 4 times 2 is 8. 8 times 2 is 16. What if I plug that in? What if I plug in 2? 4 times 2 to the second power. This means multiply 2 by itself twice. 2 times 2 is 4. 4 times 4 is 16. So it checks out, but I know that the b value is supposed to be my multiplying pattern. So I'm going to call this my multiplying pattern, or my multiplier. Well, what's the opposite of multiplying? Because that's what I'm going to do to go backwards, is I'm going to divide by 2. 4 divided by 2 is 2. 2 divided by 2 is 1. Let's try plugging in -2 and see what happens. The negative means this should go down. So now it's 4 over 2 squared. 2 squared is 4. 4 over 4 equals 1. So that checks out as well. Knowing that the b value is our multiplier lets us figure out more values really, really fast. So now I've got 4 more points to plot. 1, 8, and 2, 16. It's going to get really steep, like exponential functions tend to do. Then I've got -1, 2, and -2, 1. And it's going to make this very steep exponential graph. And I'd like you to show that it's never going to cross the x-axis. Do not let that line cross the x-axis. Okay, this is how I'm going to graph exponential functions. So looking at the a and the b value, I can tell where the graph should roughly be. If a is a negative number, I'm going to use the bottom side of the graph. It should always be negative. If b is positive, I'm going to use the top of the graph. Sorry, if a is positive. If b is bigger than 1, it's going to grow. So the right side of the graph is going to go away. Whether that's up or down, it's going to go far steep away from the x-axis. If b is a fraction, that steep part's going to be over here, and I'm going to shrink as I go forward in time. Now for the domain and range. Domain for an exponential function, unless a word problem makes us feel otherwise, domain is always going to be all real numbers. Technically, there's no x value I'm not allowed to plug in. I can use any number as an exponent up here. The range is either going to be y greater than 0 or y less than 0? Greater than 0 is if we're above the x-axis, which we are. So that's going to be ours. Our range is y is greater than 0. It's not greater than or equal to, because this will never touch the x-axis, but it will always be above it for our graph. Now this can change. It's possible to have something added on at the end here, which would be called a vertical shift. We don't often have that, but if we do, that'll change your possible range, because that raises like the baseline of the graph. That'll be our new line that we can never cross. So that range can change, but don't expect it to during this unit, not when we're just learning. That would happen more likely in a word problem or something. So let's look at one more. Here's our last problem for this video. -1/2 to the x power. So our a value is -1, so a is negative, less than 0. Our b value is a fraction in between 0 and 1. So it's going to be on the bottom half of the graph, and it's going to be steep on the left side. And as time moves forward, I'm going to get closer and closer to 0. So that's my rough guesstimate for the graph on this one, based on those pictures from the other page in the notes. So let's start our table of values again. X and f of x. -2 to +2. And let's start with our starting value, our initial value. Our initial value is whatever a is. In this case, -1. Can you tell that that's a -1? Hopefully at this point in the year, you're comfortable saying that. So 0, -1. Well, what's our multiplying pattern? Times 1/2. Well, times 1/2 might be harder and harder for us to do over time. So what's the same as multiplying by 1/2 is dividing by 2. To cut something in half, you would divide by 2. For some of us, that might be an easier way to think of this. Anyway, that's -1/2. Then 1/2 of 1/2 again is -1/4. Now to move backwards, we would have to divide by 1/2. Well, what's the opposite of dividing by 1/2? Not opposite, but what's the multiplying version of it is times 2. To divide by a fraction, you multiply by the reciprocal. So notice that these two are also opposites. For some of us, it might just be easier to think in terms of whole numbers. That's why I'm showing both of these. So it should be getting bigger, multiplying up, as we go backwards when we have a fraction for b. This is going to be -2 and -4. Again, you can always plug these in a calculator to check them, but these ones with the fractions for b are probably going to challenge your brain the most. But these are our 5 points I'll plot. -2, -4. -1, -2. 0, and then 1, -1/2. 2, -1/4. It's getting real close. Make sure we show that that doesn't cross the x-axis, though. And then it's going to get really steep right about there. Okay, so this kind of looks like the graph I predicted. Domain and range. Domain, once again, like I said on the last problem, is going to be all reals. Range, this time is y less than 0, because we're below the x-axis. So graphing is something we'll practice a lot, just because filling out this chart, knowing where to plot your points, is a little bit of a pain. But we'll always start with predicting the shape of the graph. Sorry for the longer video, but this is a big important lesson, so hopefully you stuck with it.